Hey there, awesome physics students. Let's talk about capacitance. First of all, where does the idea of capacitance come from? It just seems like somebody pulled it out of thin air for no apparent reason. Well, let's think about some different charge configurations. So this first charge configuration is a pipe, and this pipe is coming out here, and that's the circle, and then it's got a wire in the center. So it kind of looks like this, a pipe on the outside with a wire in the middle. Let's put charge Q, positive Q on the outside and negative Q on the center. And so because the electric field is directly proportional to the number of field lines is proportional to the charge, then if I have this distribution of charges, then I'm going to get this distribution of electric field. If I then double the amount of charge on it, so I put 2Q and minus 2Q in the wire in the center, then that means I need to double the charges on the outside and double the charges, the negative charges on the center wire, which I don't have room to draw. And therefore the electric field lines will also double, which means that the electric field is proportional to the charge that I'm putting on this. Okay? Now keep in mind that the electric field is also proportional to the voltage difference between these two, because the electric field is determined by the voltage difference per spacing, or spacing. It tells you about the spacing of the equipotential lines there. So that means that the voltage is also proportional to Q. Okay, let's think about this scenario here. If I have positive Q up here, negative Q here, I get electric field like this. This is a parallel plate capacitor, the one I've been using over and over again. Now, if I double this and double the charge on the top and the bottom, that means I need to double the amount of charge here. So I have to double the amount of charge on the bottom one, and then I will double the electric field again, because remember, the number of field lines is proportional to the amount of charge on there. And so again, I get this relationship where the electric field, or the voltage, is proportional to the charge. And so it seems like there's something here that's constant in these situations that may be different between these two situations, but there's some sort of thing that remains constant about, say, for example, having parallel plates. And that constant thing is what we want to find. So to do that, we just divide these two. Now, voltage is way easier to work with than electric field, so that's why we sort of forget about electric field and we start thinking about voltage. The capacitance is defined by the charge that you can put on this divided by the voltage of that configuration. Okay? And the idea here is that if I double Q, then V will also double, and this situation, the constant for this situation, will remain the same. And the idea is that it depends on geometry only. Okay, so it only depends on the shape and size of this thing. So this is going to have a different constant than this, but whatever this constant is, no matter how much charge I put on there, that constant will only, because it only depends on the geometry, will stay the same. Now, capacitance is going to be measured in this unit called farads. And 1 farad is going to be equal to, well, this is a coulomb per volt. But because coulombs is actually kind of an awkward unit for charge, many times you'll see this measured in microfarads. And so we use this mu f. That's 10 to the minus 6 farads. Or picofarads, that's my farad, that's 10 to the minus 12 farads. Yeah, you'll see it usually in units like this. One more thing here, typically we draw these scenarios in circuits, and so when we draw them in circuits, we want to represent them we don't want to draw a picture out like this every time. So we represent a capacitor with 2 parallel plates, because that's usually the model that we use in our head, like this, and we call the capacitor, represent it with the letter C, naturally. Now, sometimes you'll connect this to a battery, and so for the battery, we draw a similar symbol, but that one has 2 parallel plates, but one is longer, and the longer one is assumed to be the positive end, and the negative is the shorter end. Now let me just emphasize that a battery and a capacitor are different things. They are not the same thing. First of all, a battery converts chemical energy into electrical energy by getting charges to move in the wires when you connect it to a circuit. Capacitors don't behave that. They're not chemical energy storage containers. They store energy in the electric field between the plates. So they're already storing it in terms of electric fields. The other difference between batteries is that, and capacitors, is that batteries, the voltage of a battery is set by the chemical reaction taking place inside that battery. So once you know the two chemicals involved, bam, that tells you the voltage of that battery. And you can't change that. On the other hand, capacitors are determined, the voltage of a capacitor is determined by how much charge you put on there. If you double the amount of charge, that will double the amount of voltage. You can keep increasing this as much as you want, as long as the material inside here doesn't break down and start shooting lightning bolts across. Then it will continue to take whatever voltage you put, up to some natural limit, of course. Or you can put a tiny voltage on here and it'll still work. Okay, so they don't work with a constant voltage. The voltage of a capacitor will change. All right.